Mm. Hello and welcome to Lab 2, the motion of a falling object. The goals for this lab is that we are tracking the position of an object that falls slower than a rock. And the point of this lab is to determine the effects of drag on real-world objects. And we are trying to prove that Newton's second law works in the y direction. And the two key formulas for this are Newton's second law and then the force of drag formula, which is A for reference area, the coefficient of drag, and the density of air times the velocity squared times 0.5. Our video is here, in which I dropped a notebook, and then we put it into Tracker, and I manually tracked all the positions of it to get the data needed to plot with our code. The top right graph is not reflective of my data. In our code, I found the mass of our notebook, and then I stated the initial position vector found on the lab. We had a change in time of 0.033, gravity is 9.8, and then B is equal to the essential coefficient in the drag equation, where we simplified the density of air times 0.5 times the reference area times the coefficient of drag, and that equaled out to be 0.076. Here I will show you our drag coefficient of a rectangular box is 2.1, and then these are the dimensions of the surface area heading towards the floor, and so we use that to calculate, and it ends up being 0.076. For the actual code, for no drag involved, you simply take out this part of the equation right here and run it, and then this will give you it. And then this part is where you add in drag. And so you add that in to find drag, and it will give you both of the equations. And then this is the graphs of our three data points. And unfortunately, the tracker is showing a much larger distance. This could be because of human error in this case. But you can see the curve relatively still follows the same curvature of this blue one, which reflects the without drag. And then you can see that the second one over here that shows it with drag is a little bit lower due to the force of air resistance. And then for terminal velocity, this is the original equation, the equation before you add a negative downward terminal force. And here you can see that it tops out at around negative 7.8 meters per second. That's its terminal velocity. And one of the what ifs was what would happen if we happen to add an extra -5 downward force and how it would affect the terminal velocity. And so we ran that in the code, and as expected, there's no change. The terminal velocity still remains around -7.8, and that's because the terminal velocity is not related to the initial speed at all. In the end, it's just whenever the forces balance out, and the force of drag is just whatever speed in the end. And that is it.